What if the key to understanding amblyopia lies not in the eyes, but in the brain? For years, we've assumed this common vision disorder stems solely from early life visual disruptions, like misaligned eyes or blurry vision in one eye. But groundbreaking research led by Dr. Mary Whitman, a pediatric ophthalmologist at Boston Children's Hospital, is flipping this narrative on its head. Her team's work suggests that amblyopia might actually be rooted in the brain's development, not just the eyes. And this is the part most people miss. The brain's wiring could be the real culprit, not the visual input itself. Amblyopia, or lazy eye, affects roughly 3% of the population. Traditionally, it's been treated as a problem of the brain favoring one eye over the other during a critical developmental window. But Whitman's study, published in Ophthalmology, reveals a surprising twist. By analyzing genetic data from over 120,000 participants in the NIH's All of Us research program, the team found that genes tied to brain development, not eye development, play a major role. This challenges the long-held belief that amblyopia is purely a visual issue. Here's where it gets controversial. The study identified 4 genetic regions and 15 specific genes linked to amblyopia. These genes aren't about eye growth or structure, as researchers initially expected. Instead, they're involved in neurodevelopment, the way the brain's neural networks form and function. As Whitman explains, changes in these genes affect how the brain processes visual differences between the eyes. This means some children might be born with subtle brain differences that make them more vulnerable to amblyopia when paired with visual imbalances. So what does this mean for treatment? Current approaches, like patching the stronger eye or using virtual reality therapy, focus on forcing the brain to use the weaker eye. But if the root cause is neurodevelopmental, these methods might not address the full picture. Whitman's findings hint at a future where treatments are tailored to a child's genetic profile. Imagine therapies that target the brain's unique wiring, not just the eyes. But here's the big question. Could this mean we need to rethink how we treat amblyopia altogether? For example, if a child's brain struggles to integrate visual input due to genetic factors, would traditional patching still work? Or might we need to combine it with cognitive training or even early interventions during pregnancy? Whitman's team is already exploring these possibilities. Their goal is to move beyond one-size-fits-all solutions and create personalized strategies. We want to understand each child's story, she says, because what works for one might not work for another. This research opens the door to a fascinating debate. Should we prioritize genetic screening for amblyopia? Could early detection of neurodevelopmental risks lead to better outcomes? And if so, how do we balance the cost and complexity of such tests with the potential benefits? We'd love to hear your thoughts. Do you think this study changes how we should approach amblyopia? Or are we still better off focusing on visual interventions? Share your perspective in the comments below. After all, the future of treatment might depend on the answers we're willing to ask now.